Sorry. Good evening, everyone. Welcome to Cell Talk presentation. So today, Anshuman is our presenter, and he is going to present on the topic use of AI-assisted imaging processing in healthcare. So before going to the actual presentation, let me introduce Anshuman. Anshuman Roy is working at Renix Life Sciences as a research intern, focusing on developing machine learning based solutions to analyze physiological data and monitor patient vitals. His primary responsibilities include conducting perimetric profiling of health data, utilizing vision language models for data extraction, integrating optical character recognition to digitize and process textual medical records, and analyzing medicine images data to enhance diagnostic accuracy. He is a pre-final years undergraduate student pursuing a Bachelor of Technology in Computer Science and Technology at the Indian Institute of Engineering, Science and Technology, Shivpur. He also acquired hands-on experience in developing AI-driven solutions and performing data analysis. He aspires to advance his career in the domain of artificial intelligence and machine learning. So I welcome Anshuman to give his presentation.
Thank you for joining us today. I'm honored to present on this topic of use of AI-assisted image processing in healthcare. Let's explore how artificial intelligence is revolutionizing medical imaging and transforming patient care. Let's start with the introduction and the significance. Let's begin with an overview of the significance of AI in medical imaging. First, let's consider the staggering volume of medical imaging studies. Over 4 billion scans are conducted annually worldwide. The immense volume underscores the critical need for rapid and reliable interpretable tools to manage and analyze data effectively. Next, we face increasingly complex diagnostic demands. With the proliferation of advanced image modalities like MRI, CT, PET, and ultrasound, clinicians must process multidimensional data swiftly and accurately. This complexity necessitates sophisticated analytical methods where AI can play a pivotal role. AI's transformative potential is evident in recent clinical trials within radiology and cardiology, demonstrating significant reduction in misdiagnostics where AI-assisted tools with human experts. Furthermore, the AI in the healthcare market is projected to soar to around US$ 356 billion by 2032. This growth is driven by advancements in software, hardware, and services, with applications ranging from virtual assistants and diagnostic tools to robot-assisted surgeries. This is the growth of the AI healthcare market globally. It has a CAGR of 37.66% every year, and it is expected to be at 356 billion by 2032. Now, here is our presentation roadmap outlining the key sections we will cover today. We will start with an introduction and discuss the significance of AI in medical imaging. Then we will delve into the importance of medical imaging in healthcare, followed by the historical evolution of AI-assisted imaging. Next, we will explore the technical framework of AI-assisted image processing to examine core AI techniques utilized in medical imaging. We will discuss the clinical applications across various specialties supported by representative case studies. Following that, we will evaluate the performance metrics and statistical outcomes of AI tools, discuss ethical and regulatory considerations, and address challenges and limitations faced by AI integration. Looking ahead, we will explore the future horizons of and emerging trends in AI-assisted medical imaging, and finally conclude our session with that. Medical imaging is the foundation of modern diagnostics, underpinning approximately 80% of hospital diagnostics, guiding critical decisions. However, the mounting data complexity poses significant challenges. With higher resolution scammers and advent of 3D imaging techniques, practitioners now handle vast and intricate datasets daily. This complexity often exceeds human capacity for meticulous review, highlighting the need of advanced AI-driven analytical tools to enhance diagnostic accuracy and efficiency. As illustrated in the figure, medical imaging encompasses various modalities and serving unique diagnostic processes and contributing to comprehensive patient care. Now, let's trace the historical evolution of AI-assisted imaging. From the 1960s to the 1980s, early AI models utilized rule-based systems with fixed algorithms to interpret medical images. These pioneering tools were inflexible and primarily confined to research settings. However, they laid the groundwork for the modern clinical application tools like computer-aided detection systems and much more. In the 1990s and 2000s, we saw an advent in the revolution of digitalizing imaging, and mainly the advent of PACS, the picture archiving and communication system. This digital revolution introduced widespread use of X-rays, CT scans, and MRIs, streamlining the storage and sharing of digital images. PACS enabled the collection of large data sets essential for training more advanced AI models, thereby enhancing diagnostic capabilities. Transitioning into the 2000s and 2010s, we saw integration of machine learning algorithms such as support vector machines, random forests, into medical imaging. These models improved patient recognition and also diagnostic accuracy, particularly in tumor detection and classification, making AI tools more reliable in clinical settings. The deep learning boom was particularly the most important boom in this industry. The deep learning boom from the 2000 to the present was driven by the GPU acceleration and the availability of large annotated datasets. This era revolutionized AI-assisted imaging with high accuracy and image analytical tasks. A landmark achievement was FDA's approval of IDXDR in 2018, the first autonomous AI diagnostic system for diabetic retinopathy screening. In 2020s, we saw the advent of multimodal AI integration, beginning combining imaging with other data sources like genomics and electronic health records. Transformer-based models facilitate this integration, enabling comprehensive and personalized diagnostics. In the same time, we saw the advent of regulatory and ethical milestones. As AI technologies advanced, robust regulatory frameworks like the FDA software as a medical device, SAMD guidelines were established, emphasizing data privacy, informed consent, and algorithmic transparency. These measures ensured that AI applications in medical imaging were deployed responsibly and ethically in the healthcare environment. This diagram shows the timeline showcasing the transformative milestone in radiology and computing. This convergence of technology has revolutionized medical imaging and healthcare. This is a particular case of X-rays, like how the X-ray developed and how the AI technologies and computers developed and how they converged into the modern thing. The biggest milestone here is the first FDA-approved AI-based algorithm, which was developed by the company of Arteris. It was an algorithm for MRI scanning, and it laid the foundation for AI-assisted healthcare. This is another very key step in evolution of AI-assisted imaging, PACS, Picture Archiving and Communication System. PACS networks streamlined medical imaging workflows, integrating modalities, storage, and viewing of efficient diagnostics. It ensures seamless connectivity between radiologists and healthcare systems. It provided a digital solution for storing, retrieving, and sharing of medical images. It replaced the traditional film-based system, enabling faster and more efficient workflows. It followed particular DCOM standards for seamless communication between imaging and devices and a system. And the main thing that it contributed to the data that the modern AIs are trained on. It laid the foundation for AIs to be trained on later. What can I say? Like starting a generational flow. This is the technical framework of AI-assisted image processing. Like generally, it starts with data acquisition and pre-processing. There is a simple quote here: garbage in, garbage out. So we need good data. We need to pre-process the data well. Then we need to annotate and label the data properly. These are done by the field experts. Then we need to train the model and validate that particular model. Then we deploy the models and run it on a continuous feedback loop with more data coming in. This continuous learning system updates with the new data, refining predictive accuracy and adapts to the changing critical standards over time. Now let's explore the technical framework of AI-assisted image processing. At the core, several AI techniques are employed to analyze and interpret medical images effectively. First, let's start with the convolutional neural networks. Convolutional neural networks dominated this domain for over 10 years. The biggest power of convolutional neural networks is to understand intricate patterns in a hierarchical manner. It excelled in classification and segmentation tasks, achieving over more than 95% accuracy in breast cancer detection and reducing diagnostic errors by 20 to 30%. The advent of GANs, generative adversarial networks, which generate realistic synthetic images to tackle data scarcity and improve models' robustness. GANs-based augmentation has increased melanoma detection rates by 8% in recent rates, enhancing training datasets and models' performance. If we go over the first image here, this is an image of the low-dose CT scans. Low-dose CT scans are particularly healthier than the high-dose CT scan for human body because they are in a lower dose, but they have the problem of being noisy. GANs have been particularly effective in denoising this kind of images, which helps medical professionals and other AI tools to find out the errors or problems. Now, here we have another image showing the progression of breast cancer from early detection to malignancy. AI tools trained over time series of data sets from earlier diseases and how they progress can help in early detection of multiple diseases, which can be missed very easily by clinical professionals and doctors. Then the advent of transformer-based models shown that how we can mix multimodalities with imaging to have better performance. The object detection algorithms are particularly used to identify and specify identify and locate specific objects within images with bounding boxes. The applications include detecting nodules in CT scans and organ localization for surgical planning, improving lesion localization accuracy, and accelerating diagnostic progress. This is an image that is a sample results obtained by YOLO V7, which is a very popular object detection algorithm, displaying firm and soft melanoma tumor detection and classification with different confidence values. This can help clinical professionals and doctors to identify and detect particular diseases within the entire scans and the medical imaging. Image segmentation techniques. Image segmentation techniques partitions images into meaningful segments corresponding to the anatomical structures and the pathological regions. This is essential for delinearizing tumor boundaries in MRI scans and for organ segmentation in radiation therapy, enhancing treatment planning and precision. This image is a 3-axis visualization of MRI data of brain. The first one is axial, the second one is coronal, and the third one is sagittal. The colors indicate the regions of tumor here. Red is for necrosis and non-enhancing tumor. Yellow is for enhancing tumor, and the green is for edema, the fluid that is inside the brain. This shows that modern AI tools can segment and detect the boundaries of tumors and cancers very effectively, which can help surgeons in their operations and in multiple fields. Another important tool is the OCR, optical character recognition. It extracts textual information from scanned documents and images. It utilizes in digital medical records and automating report generation. It reduces the manual data entry time and increasing data accessibility and workflow efficiency. The image that is shown here is a simple example of how it is used. OCR can extract key information from any patient report or any document very seamlessly, increasing the time it requires for this documentation in medical processes. Another important advent is the clustering algorithms. Clustering algorithms group similar data points based on feature similarity without predefined labels. Applications include patient stratification, image grouping, and anomaly detection, enabling personalized treatment plans and improved patient outcomes through tailored intervention. Finally, anomaly detection identifies deviations from normal patterns in imaging data, indicating potential pathologies. It is used in early detection of diseases and quality control in imaging equipments, facilitating proactive healthcare interventions and reducing disease progression rates. This is an image that is very popular in anomaly detection. It shows that how how a pneumonia lung and a COVID-19 lung X-ray is different from a normal X-ray. By these kind of images, AIs can detect the particular diseases quite easily. Now let us dive into the clinical applications. AI's clinical application spans over multiple medical specialties, significantly enhancing diagnostic accuracy and operational efficiency. In radiology, particularly, AI-driven software enhances ECG analysis by accurately measuring left ventricular ejection fraction and wall thickness, maintaining high consistency with cardiologist assessments. AI algorithms also detect arrhythmia such as atrial fibrillation or ventricular tachycardia from ECG waveforms, achieving near expert performance in some smartphone-based applications also. Additionally, predictive models integrate imaging parameters with patient histories to forecast heart failure risks and aiding proactive interventions. As illustrated in this figure, this is a very popular convolutional neural network named AlexNet, which has been shown to detect anomalies, or what can I say, classify ECG signal into multiple categories via the transformation known as the continuous wavelet transform, CWT. Next, in the clinical applications of dermatology, the first thing is the skin lesion classification. Deep learning frameworks categorize lesions like melanoma, NABI from dermatoscopic images. A recent meta-analysis found AI sensitivity of 92% in melanoma screening. There are smartphone diagnostics like patient-friendly apps which empowers remote checks. This is especially benefit in underserved areas, allowing early detection and referral to specialists. Like visual pattern recognition, consistent quantifiable evaluation in lesion shape, color, and texture reduces the subjective variability among clinicians. Like these are the two images of AI being able to detect very minute details in the skin. Next comes ophthalmology. The biggest thing in ophthalmology is diabetic retinopathy screening. AI algorithms automatically detect retinal abnormalities such as microaneurysm and hemorrhages, enabling early diagnostics and timely interventions to prevent vision loss. Macular degeneration. AI analyzes OCT scans to identify subtle drusen deposits and other early signs of age-related macular degeneration, facilitating prompts and personalized treatment plans. This image is actually a very interesting image. It shows the segmentation of optic curve and optic disc in glaucoma patients. As you can see, in non-glaucoma cases, there is a big difference between the optic cup and the optic disc, leading to bigger NRR regions. But in glaucoma patients, the optic curve and optic disc almost coincide, showing a very small NRR regions. These segmentations can easily detect glaucoma and is widely used in glaucoma detection. In pathology, whole slide imaging analysis, like digitalizing histopathology slides and high resolution transforms them into data for AI to process, often pinpointing cancer cells up to 95% accuracy. Cell counting and classification, automated systems for highlighting regions of interest, accelerating tasks like counting tumor cells, quantifying immune fibrillates, and gauging malignancies. Collaborative networks, worldwide digital slide sharing fosters research, second opinions, and improved diagnostic corresponding rates among pathologists. Yeah. Now, let's delve into this representative test case study that highlights AI's practical impact in diabetic retinopathy screening with IDXDR. IDXDR was the first autonomous AI diagnostic system that was approved by the FDA. It is designed to detect diabetic retinopathy without the need of a specialist to interpret the results. Developed by the IDX technologies, the system utilizes deep learning algorithms to analyze retinal images captured by fundus photography. By automating this detection process, IDXDR enables early diagnostic and timely interventions, significantly reducing the risk of vision loss in diabetic patients. This case study exemplifies how AI can seamlessly integrate with clinical workflows, enhancing diagnostic capabilities and expanding access over essential eye care services. Now, evaluating the performance and the performance metrics and statistical outcomes of AI-assisted image processing is critical to understanding its efficacy and its reliability. Now, first, let's start with sensitivity and specificity. AI algorithms achieve high diagnostic accuracy by effectively identifying true positives and minimizing the false alarms. This readability enhances disease detection and ensures clinicians can trust AI-assisted diagnostics. Now, coming to the clinical workflow impact, the integration of AI seamlessly streamlines clinical workflows by accelerating image interpretations and reducing repetitive tasks. This allows healthcare professionals to focus on more complex tasks, thereby improving overall efficacy and patient care quality. Now, coming to validation methods, comprehensive validation through cause validation, external testing, and clinical trials ensures that AI tools perform reliably in diverse world settings. These rigorous validation methods distinguish reliable AI tools from experimental models, fostering trust in clinical environments. Now, seeing a case success, successful implementations of leading hospitals demonstrates that AI ability to enhance diagnostic confidence and operational efficiency. These real-world deployments lead to improved patient management outcomes and showcasing AI's intangible benefits in healthcare settings. Now, coming to the ethical and regulatory considerations. Now, if you see this image, this shows the healthcare data breach statistics over the years. As you can see, this is having a very increasing trend, particularly on data frame hacking of hospitals and of data leaks and all these terms. So in this criteria, ethical and regulatory considerations play a huge role. The patient privacy and data security is a must. Compliance with HPAA, GDPR, and local regulations is mandatory. Data breaches can undermine public trust in AI solutions. There should be an informed consent with patients. Patients should be aware of the AI's role in diagnostic and how their data might be used for algorithm training and improvement. And the last, but not definitely the least, there should be reliability and accountability. Clear guidelines are needed to determine who holds responsibility when an AI-based decision leads to error: developers, clinicians, or hospitals. Despite the immense potential, AI integration in healthcare faces several challenges, limitations, and pitfalls that must be addressed for successful and sustainable adaptation. The first and the foremost is data quality and bias. AI models require diverse and high quality data to function effectively. A large and diverse data can lead to bias. A lack of diverse data can lead to biased models that may misdiagnose underrepresented populations and extravagance healthcare disparities. Then there should be algorithm transparency. Most of the models are kind of treated as black boxes. We don't know how they are doing what they're doing. So explainable AI frameworks are in development, which is a must to understand how the AI is reaching the particular solution to help clinicians and doctors trust its process and its results much more. The last and definitely a very key factor is regulatory hurdles. Obtaining FDA or CE approvals can be time consuming. However, this process ensures patient safety and product reliability. Now, coming to the future horizons, looking ahead, several future horizons and emerging trends are set for further revolutionizing of AI-assisted medical imaging and healthcare delivery. Firstly, the integration of AI in robotics promises unprecedented precision in surgery. Precision surgery with real-time imaging guidance offers sub-millisecond latency. Like this image that we have here is a Da Vinci surgical system. It is an AI-assisted robotic tool that can help do microsurgeries very easily. The second is multimodal data fusion. We must combine imaging with genomics, AHD data, which can yield personalized treatment plans, can improve patient outcomes greatly. Then there is AR and VR applications. Augmented reality overlaps can guide surgeons through complex anatomy, potentially reducing surgical complications by notable margins. Now, coming to the conclusion, to conclude, AI-assisted image processing has a transformative impact on medical imaging, significantly enhancing diagnostic accuracy, optimizing workflow, and expanding access to equitable healthcare. By enabling early detection and efficient resource allocation, AI is revolutionizing patient care. However, addressing challenges such as ensuring data quality and diversity, establishing robust regulatory and ethical frameworks, and prompting algorithmic transparency is critical for sustainable integration. These measures are essential to prevent biases, ensure safe deployment, and foster clinical trust, enabling effective human-AI collaborations. The final takeaway is that AI-assisted image processing drives innovation in healthcare by improving patient outcomes and operational efficiency. Success and responsive integration relies on collaborative effort and adhere to ethical standards, ensuring that AI technologies deliver safe, effective, and equitable healthcare solutions. Thank you all for your attention. I'm open to questions and discussions that you might have now.
Thank you, Anshuman, for your presentation. Audience, now the floor is open for any queries. You can type your queries in the chat box. And Anshuman, we already have one question from Vijay sir. How does the accuracy of AI diagnosis compares with the expert human?
There are two aspects to this answer. Now, first, if we compare like different images, sometimes there are very subtle things that can be even mixed by expert humans, which can be detected by AI. Furthermore, the biggest advantage of AI is that an expert human can only iterate through a limited amount of data, whereas AI can process much bigger chunks of data simultaneously, which can help diagnostics of a bigger audience and a bigger population of patients.
Yeah, thank you. Any more questions from the audience? Yeah, I don't see any further questions. Will you please move to the last slide? Yeah. So next presentation will be on how families' use of digital technology can be a tool for reducing loneliness and improving food intake among older adults. And this presentation will be given by Divya Lakshmi Ramakrishna on 5th of February 2025. And I thank everyone for attending this session, and I hope to see you all again in the next session. Thank you, Anshuman.